about the periodic activity monitoring system. That is a project working on with Dr. Cheechin and Dr. Jafari, two research professors on campus. I'm joined by my colleagues, Tyler, Mark, and Tree. The only EE of these three being Tyler. I'm also a CE. So the periodic activity monitoring system is actually a device that is planned to be a wearable, batteryless, low-power device that can track movements real-time at a stream, as a stream of data constantly, and actually identify specific movements real-time, reporting to the user you use these movements. The specific application that Dr. Cheechin and Dr. Jafari have in mind is perhaps in a medical device that could track, actually could find early symptoms of, say, Parkinson's and report that to the user. It could also include like an elderly person wearing it, and if they fall down the stairs, it would say, this person fell down the stairs. You know, things like that. That's the future of this device. When we actually came into the design, they were nearing the end of initial design. They had 3 different designs set up. They had block diagrams. They were nearing the end of coding. So we actually had the choice of which design we wanted to join on and aid in designing by testing on FPGA. So we actually chose one that was heavily based on granular decision-making paradigm. And what that is you can see we have somewhat 2 stages. The first stage takes in a signal with very high decimation. It's looking at the signal. We do this to save power. However, once we say, yeah, this is a signal we want to keep looking at, and we get to the second stage, we decrease decimation, therefore looking at the sample in more detail, making more comparisons, and being able to make a more accurate assessment. Is this the movement that we want to identify? So, once we got our code, we actually started by just trying to dry run the entire system. However, it became pretty clear initially that we weren't getting results we were expecting. A lot of control signals weren't firing at the right time. So we actually had to break down the entire system into blocks of code based on functionality. The first system we looked at was the DTW block. DTW is actually an algorithm that can be used to compare 2 signals in time. It stands for dynamic time warping. So it literally means you can look at a signal that's 6 seconds and compare it to a 2-second signal, and you can find similarities. This allows for margins of error in terms of someone moving slower than another person. In working with the DTW block, we've actually had a lot of success. We've been able to fully implement it on an FPGA. We first verified, of course, using simulators on multi-sim. And so looking forward, since we have the DTW block functional, we want to try and, of course, implement it into the full system and get the full system onto the FPGA. It should also be noted that so far, the majority of our testing has been done using hard-coded inputs. We haven't yet successfully gotten the built-in accelerometer of the FPGA to talk properly with DTW. So that's also a good primary goal. Ideally, if we can finish all of this before into next semester, we would also like to start helping with the form factor. Initially, obviously, it needs to be a small device going on the wrist. So actually, if anyone has any questions, go ahead and open that up.
So you're implementing this all in FPGA. What language are you guys using?
All the coding was done in Verilog, and we're actually using the RTX 7, Nexus 4 of the RTX 7 side instance.
How did you decide on Verilog?
It was actually just